In part 2 of this presentation, we're going to see how to change the multipoint parameters to solid load parameters so that we can use the same global deflection equation for solid loads. We'll start off by introducing the concept of load vectors. The vectors u and v, which have just been defined, contain information about the magnitude and position of each point load, and so will be referred to as load vectors. Load vector v depends on S, the total number of point loads, which in turn depends on the load width d via the equation d equals S minus 1b. And as d is constant in any given situation, so is load vector v. Load vector u depends on r, which in turn depends on x through the inequality ar is less than or equal to x is less than or equal to ar plus 1. To evaluate these load vectors, we need only look at one of them, as they both behave identically, apart from the endpoint r or s. Looking at load vector u, this is defined as the sum of fm times vector am from 1 to r, and we've already seen that we can write fm as alpha minus beta am, and vector am is equal to 1 am squared, am cubed. The summation is over m, but we have AMs, so we need to convert the AMs into M's before we can carry out the summation. This is easily done, as we've already seen that AM can be written as A plus M minus 1B, and I can take out the M term to give A minus B plus MB, which I can rewrite further as B lambda plus MB, where lambda is a new parameter defined to be equal to A minus B over B. I'm now in a position to carry out the summations, which I'll do using the standard result shown below. I'll carry these out in a particular way, as I'll show in the sum of AM from 1 to R, which is the same as the sum of B lambda plus MB from 1 to R. The first term, B lambda, doesn't contain any powers of M, so the result is just B lambda R. The second term contains a single power of M, so the result is a half r into r plus 1b. If I take out a half b from each term and expand the remainder, I get 2 lambda r plus r squared plus r in brackets. The first two terms can be written as r plus lambda all squared minus lambda squared, and the remaining r term can be written in the same fashion as r plus lambda to the power 1 minus lambda to the power 1. I know I don't need to put the 1 in here, but I want you to see that the pattern is the same as the preceding term. If we introduce a new parameter, big R bracket n, where n is put in brackets to signify that it isn't a power but an index, then big R bracket n is equal to r plus lambda to the power n minus lambda to the power n. The summation of am can then be written as a half b into big R bracket 2 plus big R bracket 1. To simplify things, I'll call this R2, where Rn is defined to be the sum from 1 to R of am to the power n minus 1. As you can see, there's a pattern here, in that to go from the sum of m to the power n to am to the power n, we let small r to the power n go to big R bracket n and multiply everything by b. Using the notation defined in the previous slide, we can write the summations from 1 to r of powers of am as shown below, where big R bracket n is defined to be equal to small r plus lambda all to the power n minus lambda to the power n, and where big R subscript n is equal to the sum from 1 to r of am to the power n minus 1. We can do the same for load vector v, where in this case the summations are from m equals 1 to s, and define an equivalent parameter big S bracket n, defined to be equal to s plus lambda to the power n minus lambda to the power n, with big S subscript n equal to the sum from 1 to s of am to the power n minus 1. When using the global deflection equation, both of the terms on the right hand side contain a vector matrix vector product, which has to be evaluated. This is done on the component level. For example, UAX can be written in component form as UI, AIJ, XJ, where the I and J are dummy variables running from 1 to 4, And this is how these vector matrix vector products are carried out. So it's the components of load vectors u and v, un and vn that are important, not the vectors themselves. So if we look at load vector u, again we need only look at one as the other behaves the same way, then we know from the definition that it can be written as the sum from 1 to r of alpha minus beta am times vector 1 am squared am cubed. If we look at the first component of vector u, u1, then this is just alpha minus beta am times 1, or alpha minus beta am. Using the results shown in the previous slide, we can write this sum as alpha times big R1 minus beta times big R2. If we look at u2, which is equal to alpha am minus beta am squared, we'd find that this summation would give alpha big R2 minus beta big R3. This is easily generalized to un is equal to alpha big Rn minus beta big Rn plus 1. Similarly, we find that Vn is equal to alpha big Sn minus beta big Sn plus 1. Components Vn depend on big Sn, which depend on small s, which depend on d, which are constant, and so therefore are the Vn. Components Un depend on big Rn, which depend on small r, which in turn depends on x through the inequality ar is less than or equal to x, less than or equal to ar plus 1. We need to find this relationship between r and x. If we look at the diagram to the left, which we've seen a few times before, where x lies somewhere between the rth and the r plus 1th point loads, then we can write that x is equal to a plus r minus 1b plus a fraction of b, depending exactly where x lies. If we introduce a new quantity e, which is greater than or equal to 0 and less than or equal to 1, then we can specify the position of x between the 2 point loads as eb. So we have x equals a plus r minus 1b plus eb. We don't in fact need to bother with the term eb, as it will be made to vanish when we go over to solid loads, but I'll put it in to be accurate. I can rearrange this to give r is equal to x minus a plus b all over b minus e, and if we introduce a further new variable, big X, where big X is defined to be equal to small x minus a plus b, then I can write the dependence of r on x in the form r equals big X over b minus e. Note that both un and vn contain the load spacing b, either explicitly or implicitly, and so are only valid for multi-point loads. For the un and vn to be applicable to solid loads, the b's must disappear. In order to go from a multi-point load to a solid load, we let the interload spacing b go to 0, whilst keeping the load width d a constant. When b goes to 0, the term that has the largest power of b in the denominator will dominate the others, and any b's in the numerator will vanish. So lambda, which is defined to be a minus b over b, loses the b in the numerator and becomes a over b. S, which is equal to d over b plus 1, goes to d over b, as this becomes much larger than 1 when b goes to 0. Big X, defined to be x minus a plus b, just goes to x minus a, and r, equal to big X over b minus e, goes to big X over b, which is the same as x minus a over b. Similarly, r bracket n goes to x to the n minus a to the n over b to the n, and s bracket n goes to d plus a to the power n minus a to the n all over b to the n. R subscript n and s subscript n simplify greatly when b goes to 0. For ease of use, I'll just refer to these as Rn and Sn from now on. For example, S3, which is the sum from 1 to s of am squared, is given by earlier results as a sixth b squared into 2s bracket 3 plus 3s bracket 2 plus s bracket 1. Multiplying out the three terms in the square bracket, the first term contains b squared times s bracket 3. We can see from above that s bracket n has b to the power n in the denominator, so s bracket 3 has b cubed in the denominator. When multiplied by b squared in the numerator, the result is a single power of b in the denominator, making this term order 1 over b. The second term in the expansion multiplies b squared by s bracket 2, which has b squared in the denominator, and so the b's in the numerator and denominator cancel, making this term order 1. The last term multiplies b squared by s bracket 1, which just has a single power of b in the denominator. The result is a single power of b in the numerator, making this term order b. As b goes to 0, the order b term goes to 0 identically, and the order 1 term becomes insignificant when compared to the order 1 over b term, so this can be ignored, leaving only the order 1 over b term. This came from the first term in brackets, the s bracket 3 term. This is a general result when evaluating Rn or Sn as b goes to 0. The only term that survives is the one with the highest number in brackets. In this case, S3 goes to a third b squared s bracket 3, from which we can generalize Sn to 1 over n b to the power n minus 1 times s bracket n. Similarly, Rn goes to 1 over n b to the power n minus 1 times r bracket n. Using these results, we can see how un behaves as b goes to 0, and similarly how vn behaves. We've simplified all the beam and load parameters as b goes to 0, as well as the formulae for un and vn, but they all still contain a single power of b in their denominators. In the next slide, we'll see how we can get rid of these. At the end of the last slide, we ended with these formulae for un and vn, resulting from taking the limit as b goes to 0. Each term still has a single power of b in the denominator. We can get around this by defining new load parameters for solid loads, alpha s and beta s, which are defined to be equal to alpha over b and beta over b respectively. When we do this, the b's in the denominators for un and vn disappear, and we have alpha s and beta s instead of plain alpha and beta. These formulae can now be used for a solid load. We effectively absorb b into alpha and beta when we go from a multi-point load to a solid load. But we now have to carry around two different versions of alpha and beta, one with the subscript s for solid loads and one without for multi-point loads. And as the goal was to develop a global equation for solid loads, I'm not really interested in multi-point loads, so I'm going to keep the new formulae for un and vn and drop the subscript s from alpha and beta. There won't be any confusion with the original alpha and beta, as I'm not going to bother with multi-point loads from now on. By absorbing b into the definitions of these new alpha and beta, we also affect the definitions of the other load parameters as we go from a multi-point load to a solid load. For example, beta, which was defined to be delta f over d, where delta f was the difference in the endpoint loads f1 and fs, now becomes delta w over d, where delta w is the difference in w1 and ws, where w is the load per unit length of a solid load. Similarly, in the definition of alpha for a multi-point load, f1 and fs become w1 and ws when we move to a solid load. R, which was equal to big X over b as b goes to 0, now becomes just big X, and S, which was equal to d over b as b goes to 0, now becomes just equal to d. By redefining these parameters in this way, we can now apply the global deflection equation to solid loads. In this slide, I have quickly summarized the main points of the global deflection equation for solid loads and introduced some new notation to streamline the formulae. First of all, we have the standard form of the global deflection equation in terms of the load vectors u and v, the beam independent matrix A, and the beam dependent quantities j, p, and dt. In the last slide, we saw how to write the components of the load vectors un and vn in a form appropriate for solid loads. These equations can be written in a more compact form if we introduce some new notation. If we define square bracket n as being equal to d plus a to the power n minus a to the power n, or divided by n, and curly bracket n as x to the power n minus a to the power n, or divided by n, then we can write un in the simple form as un equals alpha curly bracket n minus beta curly bracket n plus 1, and vn as alpha square bracket n minus beta square bracket n plus 1. As well as being more compact, this form also shows up the symmetry between un and vn, where they can be transformed into each other by changing a curly bracket to a square bracket or vice versa. As un and vn both contain the linear load quantities alpha and beta, these new formulae for un and vn apply to linear loads only. Using the new compact form for un, we see, for example, that u1 is equal to alpha curly bracket 1 minus beta curly bracket 2. Then using the above definition of un, this can be written as alpha into x minus a minus beta into x squared minus a squared all over 2. Similarly, v1 is equal to alpha square bracket 1 minus beta square bracket 2, where square bracket 1 is equal to d plus a minus a, which is equal to d, and square bracket 2, which is equal to d plus a squared minus a squared all over 2, which can be reduced to d into d plus 2a over 2, so that v1 is equal to alpha d minus beta d into d plus 2a over 2, and similarly for the other components. As UAX is beam independent, we can derive an expression for it applicable to all beams. First we have the 1x4 row vector U, followed by the 4x4 matrix A, then the 4x1 column matrix X. Carrying out the AX expansion first, we get a new column vector with components minus x cubed, 3x squared, minus 3x, and 1. Then when we multiply this by vector u, we get the result minus u1 x cubed plus 3u2 x squared minus 3u3x plus u4. We can use this form for UAX in the global deflection equation for all loads, both linear and nonlinear, as it doesn't contain any alphas or betas. If we substitute the values of un from above, which does contain alpha and beta, we can put UAX in the form UAX is equal to minus x minus a to the fourth power times 5 alpha minus beta into x plus 4a all over 20. This applies to linear loads only because of the presence of alpha and beta. This is really all there is to the theory behind the global deflection equation and to its use for multipoint and solid linear loads. Non-linear loads need to be treated a bit differently, as we'll see shortly, but apart from that, the rest is mostly application. In order to justify the claim that this deflection equation is, in fact, a global deflection equation, valid across the whole beam, it must be able to reproduce the three regional equations, to the left, underneath, and to the right of a partial load. These are normally derived separately, but I'll show here how they are all contained within the one deflection equation. Firstly, we'll go back to the multipoint load on a generic beam and the inequality for x, namely that AR is less than or equal to x, which is less than or equal to AR plus 1, from which the deflection equation was derived. The distance to the rth point load, AR, was given by the simple relation AR is equal to A plus R minus 1B, from which we can see that A1 is equal to A. This inequality makes it look like x must lie underneath the load only, but we can show that it can exist on either side of the load as well. Starting to the left of the load, we see from the diagram that x is less than or equal to A, which is the same as x is less than or equal to A1, as A and A1 are the same. But looking at the general inequality for x, the upper bound on x here is AR plus 1. For this to be the same as the upper bound A1, R must be equal to 0. And this is the general condition to the left of a partial load. With R equal to 0, load vector U, which has R as its upper limit, must also be equal to 0, and so therefore must the product UAX. So this term in the deflection equation vanishes, and we are left with a simple deflection equation to the left of a partial load. 6EI y of x is equal to j over L to the power p times v dtx. Doing the same to the right of the load, we see that x is greater than or equal to as, where s is the last point load. Comparing this with a general inequality, we see that the lower bound on x here is AR, so AR and AS must be the same, which means that R must be equal to S. And this is the condition to the right of a partial load. When R is equal to S, the upper limit in the summation for load vector U changes from R to S, which is just the definition of load vector V. So U equals V to the right of a partial load. In the deflection equation, UAX becomes VAX, and we now have two product terms, each with load vector V multiplying from the left and vector X from the right. So we can factor these out of the equation, leaving A plus J over LP dt inside the square brackets, which is just equal to bending matrix D, from the relationship D minus dt is equal to LP over J times A, which was derived earlier. So the deflection equation to the right of a partial load simplifies to 6EI y of x is equal to j over LP v dx. Underneath the load, the general inequality holds, and the deflection equation is the standard one. 6EI y of x is equal to UAX plus j over LP v dtx. For a linear load, we can use the expression derived in the previous slide for UAX and write it in this final form. So we've seen that this deflection equation can provide all three regional deflection equations, and so the claim that it is a global deflection equation is proved. To see how these regional equations are derived in practice, consider the case of a cantilever beam having a partial uniform load. When dealing with linear loads, the first quantities to determine are the load parameters alpha and beta, and always find beta first because alpha depends on beta. In the case of a uniform load, the slope is 0, and so beta is 0. We saw in an earlier slide that alpha can be written either as W1 plus beta A or WS plus beta into A plus D. When beta is 0, alpha is equal to either W1 or WS. But as these are the same for a uniform load, we'll just refer to them as a general W. Then the total weight, big W, which is equal to the weight per unit load times the load width D, becomes equal to alpha D. Then determine the load vector components UN and VN, so that we can work out the products UAX and V dtx. As we found a general expression for UAX earlier, which we can use for all linear loads, we don't need to determine the UN, but we always need the VN. We know that we can write Vn in compact form as Vn is equal to alpha square bracket n minus beta square bracket n plus 1. But this is just equal to alpha square bracket n as beta is 0. And as alpha is equal to w, then Vn is equal to w square bracket n, or w times d plus a to the power n minus a to the n all over n. Knowing alpha, beta and the Vn, we can now determine the regional deflection equations. To the left of the load, we've seen that UAX is equal to 0, so the global deflection equation reduces to 6EI y of x is equal to j over LP v dtx, or just equal to v dtx, as j is equal to 1 and p is equal to 0 for a cantilever beam. The orange box shows the vector matrix product v dtx with the appropriate dt for a cantilever beam. The bottom two rows are all zeros, so only v1 and v2 contribute. The result is x cubed v1 minus 3x squared v2. From the equation for Vn, we see that v1 is equal to w square bracket 1, which is just equal to wd, which is the total weight of the load, big W. Note that this is always the case, that V1 is equal to the weight of the load. V2 is equal to W square bracket 2 which is W times D plus A squared minus A squared all over 2, which can be rewritten as WD into 2A plus D all over 2. Substituting these values for V1 and V2 gives the deflection equation to the left of the load as 12EI y of x is equal to minus WX squared into 3 into 2 plus AD minus 2x. To the right of the load vector U is equal to load vector V, and so the deflection equation for this region reduces to 6EI y of x is equal to V dx. We can see that the bending matrix D for a cantilever beam has zeros in the first two rows, so that only V3 and V4 contribute. The result is minus 3x V3 plus V4. Writing this first in compact form, then expanding and simplifying, results in the final form of the deflection equation to the right of the load. I won't bother reading through this as it's too long, but you can see the result. Finally, underneath the load, the full deflection equation always applies, which simplifies somewhat here as J is equal to 1 and P is equal to 0 for a cantilever beam. Here I'll use the general expression for UAX developed in an earlier slide for a linear load. As beta is 0, this simplifies to UAX is equal to minus x minus a to the 4th power times alpha all over 4. The V dtx part is the same as that for the left of the load, x cubed V1 minus 3x squared V2. And when we substitute for V1 and V2 as before, and multiply throughout by D, so that we can convert the weight per unit length, small w, into the total weight, BW, we arrive at the final form for the deflection underneath the load. These regional deflection equations are exactly the same as those obtained by standard methods. Note that if the load covers the entire beam, then A is equal to 0 and D is equal to L, the length of the beam. When the load covers the whole beam, X always lies underneath the load, so we substitute A equals 0 and D equals L in the above equation to give the result shown. This is also the same as that obtained by standard methods. This shows that we can also use the global deflection equation not just for partial loads but for full loads as well. We first get the deflection equation underneath the load, then substitute A equals 0 and D equals L.